95% of the universe is invisible to us. Not hidden, not far away, invisible right now. Passing through this room, through your body, through the screen you're watching this on. We've never touched it, never photographed it, never held a piece of it in a lab. We call it dark matter. And for the better part of a century, it's been the answer to one of the biggest problems in physics. But here's the uncomfortable part. What if it isn't? In the 1930s, an astronomer named Fritz Zwicky was studying a cluster of galaxies, the Coma cluster, and noticed something odd. The galaxies were moving so fast that, based on the visible mass in the cluster, they should have flown apart long ago. Something invisible had to be holding them together. Zwicky called it dunkel materie, dark matter. Nobody paid much attention. 40 years later, an astronomer named Vera Rubin found the same problem, but closer to home, inside individual galaxies. She measured how fast stars orbit at different distances from a galaxy's center, expecting them to slow down the farther out they got, the same way planets slow down the farther they orbit from the sun. Instead, the stars at the edges of galaxies were moving just as fast as the ones near the center, almost as if the galaxy weighed far more than its visible stars and gas could account for, as if something unseen was wrapped around it, holding it together. This became known as the galaxy rotation problem, and it's the single strongest piece of evidence for dark matter. Since then, the evidence has piled up from other directions too. Gravitational lensing, light from distant galaxies bending around invisible mass on its way to us. The cosmic microwave background, the leftover heat from the Big Bang, whose patterns only make sense if roughly 27% of the universe is made of matter that doesn't interact with light. And the bullet cluster, two galaxy clusters that collided, where the visible gas got dragged and slowed by the collision. But the mass, tracked through gravitational lensing, kept moving straight through, untouched, as if something invisible had simply passed through the wreckage. Put it all together, and the standard model of cosmology says the universe is roughly 68% dark energy, 27% dark matter, and only 5% the ordinary matter that makes up stars, planets, and us. That's the picture most textbooks give you. Now, here's where it gets shaky. For decades, the leading theory was that dark matter is a particle, specifically a class called WIMPs, weakly interacting massive particles. The idea, if dark matter is made of particles, every so often one should collide with an ordinary atomic nucleus, and we could catch that collision in an extremely sensitive detector, usually buried deep underground to block out cosmic ray interference. So we built those detectors, Xenon-1T, Lux, Pandax, Super CDMS, massive tanks of liquid xenon and other elements, shielded under kilometers of rock, engineered to detect a single particle collision in an ocean of silence. And one after another, they've come back empty. Each null result doesn't kill the theory outright, it just shrinks the space where a WIMP could be hiding, ruling out mass ranges and interaction strengths one at a time. 30 years and billions of dollars into the search, the particle we built an entire cosmological model around has never once shown up in a detector. That's not proof dark matter doesn't exist. But it's exactly the kind of pattern that should make scientists, and us, ask whether we're hunting for the right thing. Here's the idea that rarely makes it into mainstream explainers. What if there's no missing matter at all? What if gravity itself just behaves differently than we think at galactic scales? It's called MOND, Modified Newtonian Dynamics, and it was proposed back in 1983 by physicist Mordechai Milgram. The core idea is simple. Our law of gravity, whether Newton's or Einstein's, has only ever been tested and confirmed at scales we can actually measure, precisely, inside our solar system. Essentially, MOND suggests that at the extremely low accelerations found at the edges of galaxies, gravity doesn't follow the same rules it does near a star. Tweak the equation slightly, and you don't need any invisible mass to explain the rotation curves that started this whole mystery. The math just works. And it's not a fringe idea. MOND has had real predictive success. In several cases, it predicts galaxy rotation curves more precisely than dark matter models do, without needing to individually tune how much invisible mass surrounds each galaxy. So why isn't MOND the leading theory? Because of the bullet cluster. Remember that galaxy collision, where the mass and the visible gas separated? That's a serious problem for MOND. If gravity is simply modified by the distribution of visible matter, the strongest gravitational lensing should track the visible gas, the heaviest, most obvious stuff, but it doesn't. The lensing signal follows something invisible that passed straight through the collision, decoupled from the gas entirely. That looks a lot more like particles that don't interact with normal matter, which is to say, it looks like actual dark matter. So neither side has a clean win. Standard dark matter theory explains the bullet cluster beautifully, but has never produced a single detected particle after 30 years of searching. MOND explains individual galaxy rotation with elegant simplicity, but struggles badly with cluster-scale collisions and the cosmic microwave background. There's a third possibility, one that's gained traction more recently. Maybe dark matter isn't wrong, but our picture of it is too simple. Standard cosmology assumes dark matter is cold, slow-moving, and made of a single type of particle. But when scientists run simulations of cold dark matter and compare them to real observations, several small cracks show up. Simulations predict far more small satellite galaxies around galaxies like ours than we actually observe, the missing satellites problem. They predict dense, spiky cores at the centers of galaxies, but real galaxies tend to have smoother, flatter cores, the core cusp problem. And some of the largest predicted satellite galaxies appear too massive to have failed to form stars. Yet in reality, no galaxy that big exists around us, the too big to fail problem. None of these individually disprove dark matter, but together, they suggest that if dark matter exists, it might not behave the simple, uniform way our models assume. It could be warm instead of cold. It could interact with itself in ways we haven't accounted for. It could even be more than one thing entirely, a mix of exotic particles or primordial black holes formed in the earliest moments after the Big Bang, or something we haven't theorized yet. Probably not that something unseen is out there. The gravitational evidence for that is about as solid as anything in cosmology. What we might be wrong about is what it is, and how simple an answer we expect. For 50 years, the assumption has been that one clean discovery, one particle, one detector ping, would close the case. But every experiment built to find that particle has come back silent, and the leading alternative theory only solves half the puzzle. The truth might not be a single missing ingredient. It might be that dark matter is a placeholder, a name we gave to a gap in our understanding of gravity, of particle physics, or both. Decades before we had the tools to actually look inside it. We can measure its shadow with extraordinary precision. We can map exactly where it must be, down to the galaxy. What we still can't do, after nearly a century of looking, is say what it actually is. And maybe that's the real mystery worth sitting with. Not that the universe is 95% invisible, but that we've built an entire model of the cosmos around something we've never once directly seen.